All right, so welcome back to the Math of Sound. So as promised, we are looking at finishing all of the problems that are related to sound waves before we move into light waves. And right now we're on Your Own 11.3, which is at the top of page 363. So please get there. Okay, so the On Your Own. It says, a man has just said goodbye to his friend who has boarded a train. He stands and watches the train as it travels away from the station. So the source is moving away. So we're going to make a note of that. The source is moving away. Okay, so that's the first thing that I'm going to make note of. So when I pull out my note card of the Doppler effect, I know what equation I'm going to be or how I'm going to manipulate the equation that I'm going to be working with. Okay, so the train, the source, travels away from the station at 35 meters per second. So the velocity of the source is 35.0. And obviously, if the man is standing there, the velocity of the observer is 0. The train blows its horn, which has a true frequency of 411 hertz. Okay, 411 hertz. What is the frequency that the man will hear? And the temperature is 25.0 degrees. Okay, so our unknown is frequency of observer. So we're going to write down this equation incorporating the correct sign into it as we write it down. So if the source is moving away, note that color is not probably the best color. The frequency of the observer is the unknown. So being that the velocity of the source is in the denominator and the source is moving away, we're going to use a positive in the denominator. Check your notes. The source is moving away, a plus in the denominator. Okay? So the velocity of sound, plus or minus the velocity of the observer, which we know is 0. So let's just write that in. Okay, we already know what that is. And the velocity of sound, again, goes right here. And the velocity of the source is 35.0, given the true frequency is 411. So we have two unknowns here, which is just not going to work. We need to use the equation for the velocity of sound in order to get a value that goes right there, which is not uncommon for physics, is that in order to solve a main equation, which is the Doppler effect equation here, we need to use another equation to fill in one of the variables. So we are going to use the velocity of sound equation and follow the rules for using it. That's the equation for the velocity of sound. What we're going to do is fill in the temperature with 25.0. So just as a reminder, we first follow the rules for the product, then we follow the rules for addition as far as significant digits go. So the 0.606 has 3 significant digits. Likewise, the 25.0. So 0.606 times the 25.0 means that we need 3 significant digits. Assuming that you're doing this on your calculator along with me, you should see that that product is 15.15. Well, we need 3 significant digits out of that, which has us using 15.2 for our particular product there. Now, in order to get the velocity, we're going to line them up or stack them. 15.2. And it just so happens that this is going to work out very nicely. Okay, so we'll just add straight down each column, knowing that all the numbers that we get in our answer, we need to keep. Okay, so that would be 346.7, because remember, this was our significance as far as adding. Okay, now we can go back in and fill in our Doppler equation now that we know the velocity of sound. So, in fact, I'm just going to erase the whole numerator here, because when the observer is not moving, the only thing relevant to the numerator here is the velocity of sound. So plus or minus 0 is irrelevant. So 346.7. And again, because the frequency of the observer is our unknown, this whole thing will be entered into our calculator at one time. So again, if you don't have a fraction function on your calculator, open up a set of parentheses and enter in the numerator of the fraction and then divided by. Then open up another set of parentheses, and in there is where you're going to enter the denominator, 346.7 plus 35.0, and after you do that, close that set and then close the big set. In other words, if you open up 2 sets of parentheses, you need to then close 2 sets of parentheses. If you open up 2 sets of parentheses and only close 1 and continue on with the problem and hit equals, you'll get an error. Okay? So the number of parentheses that you open has to equal the same number of parentheses that you close. Okay? And then at the end here, you'll enter your 411 and then hit equals. Okay? So after you do that, regardless of what calculator you're using, you should find that the frequency of the man standing there watching the source, the train, moving away from him is 373 hertz. Okay? Easy enough. So far, the only unknown that we've had, the main unknown that we've had in the Doppler equation is the frequency of the observer. That is going to change very quickly. Like, hold on one second. So having the frequency of the observer being the unknown is going to change, like I said, very, very quickly, and that's in this next on your own. Okay? So on your own, 11.4, we're going to be using the Doppler equation, and we still have to pick out what version of that we're going to be using, but we're going to find that we're tasked with finding the value of a different unknown, not the frequency of the observer. Okay, so just for the sake of the fact that this particular problem is different, because our unknown is different, I'm going to rewrite the whole equation and then we'll fill in accordingly. So that's the true frequency. Okay, so now getting down to the reading of this. It says a woman is driving towards a factory, and as she's driving towards the factory starts to blow the whistle. So yes, I did skip over a bunch of stuff real quick, only because we need to know that the observer is moving towards the source. So if you look at your notes, if the observer is moving towards the source, and the observer is obviously the one moving, which is the numerator of the Doppler effect equation, we are going to either use the plus or the minus in the numerator. Because the observer is moving towards the source of the sound, we use a plus in the numerator. So I'm going to alter that and get rid of the minus. And that's where we are, and that's the equation we're using. Okay, so now let's look at the values that were given. A woman is driving towards the factory to pick up her husband after work. Yeah, who cares? As she travels towards the factory, which is the source, the factory starts to blow the whistle, indicating the end of the workday. The whistle's frequency is 494. That is the true frequency. So the true frequency is 494. Okay, so we're going to write that down. What she hears, what she observes, is 511. And that's because she's moving towards the source. How fast is she driving? So obviously, the velocity of the observer is our main unknown right there. And we are also given the temperature. So this problem is buried in several different unknowns, okay? First of all, the unknown is the velocity of the observer. But if we look to fill in the equation, what we don't have is the velocity of sound. So even though we had the same temperature here, okay, we're going to review the rules. So the temperature in the On Your Own 11.4 is the same as the temperature in the On Your Own 11.3, okay? So we fill in, let me change colors here. We fill in the temperature right there. And when we do the multiplication, we abide by the rules of multiplication as far as significant digits. 3 in 0.606, 3 in 25.0. So when you get 15.15 on your calculator, you will round to 3 significant digits there. Then, after you do that rounding, you will stack the two values, find the place of significance, circle it, and do the addition, rounding to that place that you've circled, okay? So we know from On Your Own 11.3 that the velocity of sound is the same. It's 346.7, okay? So we don't need to redo the whole entire velocity of sound equation. We'll just go back and use the same value from the previous On Your Own problem, okay? So now let's fill in what we've got. Okay, the frequency of the observer is 511 hertz. The velocity of sound is 346.7 plus the velocity of the observer. There's our unknown right there. And in fact, I'm going to make that red just so we recognize that that is in fact the only unknown we've got. Then you've got the velocity of sound, which is 346.7. And then, of course, the source is not moving. So we only need the 346.7 in our denominator. And the true frequency is given as 494. So that's what we've got as far as our equation. Now, the algebra here is going to be a little bit different, okay? Because the V is buried inside the set of parentheses, we need to begin to isolate that set of parentheses and have that as the only thing on the right side of the equation, which means we need to lose the multiplication of the 494. So if the 494 is being multiplied, we need to undo that multiplication by doing the opposite, which is division. Thank you. Okay, so we're going to rewrite that result, and this is what we're left with. And now that we've removed the 494, we also don't need to worry about the parentheses. So this is what we've got right now. In order to isolate eventually the V, which is in the numerator of what's on the right, we need to get rid of this. Okay, so we'll multiply that by both sides. And when we do that over here, it cancels out. So we need to multiply it over on the left. And this is what we've got on the left and the right. Okay. So now we need to isolate the V. If the 346 is positive on the right, we remove it by doing the opposite, which is to take the negative or subtract. Okay. So what the final equation will look like with our velocity being isolated is this minus the 346.7. Okay? So, again, rules matter. First, I'm going to change colors to make a point here. The first thing that we're going to do as far as the rules for significance is that bit of that equation right there. Because multiplication and division follow the same set of rules. We'll do that first and round to 3 significant digits. Okay? So again, just to find the answer here, we'll have to do this in 2 parts. So when we do that particular part of the equation and round to 3 significant digits, we'll get 359. Okay? Minus the 346.7. That is now the second rule. Okay? That's the second rule, which is subtracting. And of course, addition as well follows the same rule. So, for rule number 2 over here on the far left, we will stack these. 359 minus 346.7. And when we stack these, it makes it easier for us to determine where the significance needs to be, which is right here. Okay? So, when you pull out your calculator, 359 minus 346.7 is going to give you 12.7. Okay? Or I'm sorry, 0.3. My fault. Sorry. Okay, because that's kind of like a 0 there. So 10 minus 7 is 3. Okay, duh, right? Anyway, it gives you 12.3 because our significance is right here in our circled column. We're going to look to the 3. If that number is 5 or bigger, it changes the 2. But because it's not, we leave it as a 2 and find that velocity is equal to 12. Okay? And that's, of course, in meters per second. All right. So as far as the math of sound, those examples and on your own problems are all that we have as far as the math of sound. Everything else that follows is the math of light, which gets to be quite a bit trickier because we have several more equations, plus some of the ones that we just looked at in order to continue on with the math of light. So what you are going to do is you are going to do the practice problems tonight for homework. Okay? The practice problems that involve the math of sound. Okay? And those are, in particular, 1 through 4, all of them, and 6 and 7. Okay? So that will be due on Tuesday. And then we'll move on to the math of light. Okay? So have these ready to hand in to Mr. Asher in class Tuesday. No excuses. Okay. Awesome. Get started on those now. See ya.